what I have here is a block of 3 D-cell batteries in series. So we have a total voltage of about 4.5 volts. It's wired in series to a light bulb, which is wired in series to what's called a supercapacitor, which is just a capacitor with a ridiculously large capacitance. In this case, 0.47 farads. What I'm going to do is I'm going to complete the circuit, and I want you to predict what's going to happen to the brightness of the bulb. So go ahead and pause the video, make your prediction, and then we'll resume. Okay, here we go. Okay, so now what I'm going to do is I'm going to take the batteries out, and I'm just going to connect the capacitor and the light bulb in series. So there will be a period where the circuit will be completely disconnected, and then I'm going to reconnect it so that just the capacitor and light bulb are in series. Again, pause the video and make your prediction about what will happen. Okay, so here we go. All right, well, is that what you predicted? Let's go ahead and take a look at what's going on here. Let's start with the second of the two examples first. So we'll go ahead and take a look at a discharging RC series circuit. So we call it an RC series circuit, or just because it is a resistor and a capacitor in series. So in this case here, what we can schematically imagine, I didn't have a switch in the demo, but I just achieved that by directly connecting the wire. So we have a capacitor here in series with a resistor. And it's in series because I can run my finger all the way along and it does not go through any junctions. So we'll say initially we're holding charge Q naught on the plate, so plus Q naught minus Q naught. And then what we're going to imagine happening is we're going to close the switch. So when we close the switch, remember there is a fringe electric field. So while most of the electric field is running between the plates, going from the positive plate to the negative plate, there is a fringe field that loops around like so. And importantly, when I close this, the fringe field will align itself to follow this conductive pathway. And so in so doing, it will start moving charges around the circuit, and we will induce a current, like so. Now, what that's going to mean is as we go on, the value of the charge I have on the plates is going to decrease, because what I'm doing is remember, the electron flow is the opposite direction. I'm taking electrons off of this plate, moving them here. That's reducing the strength of the electric field. Reduce the strength of the electric field, I can't push on the mobile charge carriers as hard, which means I can't drive as much of a current. And so that's what you were seeing happen. Initially, when I hooked up the batteries to the when I initially hooked up the capacitor to the light bulb, the charged capacitor, we saw that the light bulb was really bright, and just sort of pulling a big current, but that the charges here did come from somewhere. So this is different than a battery. The battery, the chemical reactions of the battery just keep shoving charges along. Here we truly do have stored charges, and the charges are coming from the plates of the capacitor. And as we flow the current, the magnitude of the charge will decrease. And we also saw that the light bulb was dimming. And this is because the electric field strength throughout the wire is decreasing, which means we can't push the current as hard. Now, just to give the very slight flavor for how to do this, we can analyze this with Kirchhoff's loop law, but I'm going to have to wave my magic wand a bit. So if I imagine walking my dog around the circuit clockwise, my metaphorical dog, as I go from the negative plate to the positive plate of the capacitor, it'll increase by, if we remember Q equals C delta V, it'll increase by Q over C. And then I go through the resistor following the direction of the conventional current. There'll be minus IR. I get back home, I write equals 0. Now, at first you don't think you could do much with this, but we recall that that the current here, or we'll observe that since the current is coming from the plates, this will be equal to, and I have to throw in a minus sign, delta Q over delta T, where Q is the charge held on the capacitor. Now, since we are decreasing charge as our charge is decreasing as a function of time, our current is positive, I gotta stick in a minus sign for bookkeeping. All right, so we can combine these and use the methods of calculus. So we'll define a quantity called the time constant. This is tau, same symbol we used for torque back in mechanics. We're starting to recycle our letters here. And this will be equal to the product of the resistance and the capacitance. Believe it or not, if you multiply an ohm and a farad, grind through all the unit conversion for yourself to prove to yourself that that product is seconds. What we will also get is that the current will equal whatever the initial current was through the circuit, which you can just get by twinkle twinkle little star, delta V equals I times R, times e to the minus t over RC, t over tau. And here, this E is not the charge on the electron. It's the base of the natural logarithm, 2.718281828. If you prefer, you can write it as I naught exp minus t over tau. And many calculators will actually label the button exp. They'll either label as e to the x or exp. Same difference, just depends on your maker model of calculator. We will also get that the voltage across the capacitor will be whatever it was initially. So this is a naught for initial. Naught is British for 0. So this is actually a tiny little 0, but it just means the initial value, just like this is the initial current. And again, times e to the minus t over, minus t over tau. And finally, if you just multiply through by c, you'll get that the charge as a function of time will be whatever the initial charge was times e to the minus t over tau. So hopefully this makes some sense. We're seeing that the rate at which I can pull charges off depends on the, so here, this I is the rate at which I can pull charges off the capacitor. And we can see that it depends on the charge on the capacitor itself. And this sort of thing occurs all over the place. It'll occur in radioactive decay. It occurs in certain kinds of pharmacokinetic relations in medicine, for instance. It shows up in a lot of places where the rate at which you can get rid of something is proportional to the amount of stuff you have in the first place. And for any of these cases, the answer will always look like this. So, kind of the benchmarks that I have here for thinking about this is that a fully charged capacitor acts like a break in the circuit. And that's because it is a break in the circuit. That's because if it's fully charged, you literally can't move any more charge anymore. And remember, with a capacitor, there is nothing between the plates. So it is now truly a break in the circuit. A completely discharged capacitor momentarily acts like a wire. And by this I mean, I'm going to put that in quotes. And again, this is because no current is going to flow between the plates ever. But because there's no charge on the plates, there's no potential difference across the plate. And so that's the same thing from a voltage perspective as just having an ideal wire. Now, some benchmarks to think about this. So for instance, I can go ahead and plot, it doesn't matter whether it's the current or the charge or the voltage. In this case, all the graphs look the same. So let's just go ahead and do the charge. All of these graphs will have the same kind of behavior. And that is if at time 0 I throw the switch, I will have had my initial charge on the capacitor, and it will fall off exponentially, asymptotically approaching 0. So it's approaching 0. It'll never get there, but depending on what you're trying to do, good rule of thumb, after 7 time constants has elapsed, it's usually 0 enough. An important number to remember here, sort of our magic number, if you will, is 37%. So after 1 time constant has elapsed, so say tau, the charge will be at 37% of what you had initially. After 2 time constants, it will be at 37% of 37% of what you had initially, so 0.37 squared. And I think you get the idea. After 3 time constants, it'll be 37% of 37% of 37%, so 0.37 cubed of what you had before, and so forth. This is called an exponential decay behavior. So that's how we can interpret the time constant. It's the time it takes to go from where you started to 37% of where you started. Why 37% and not something more convenient? That just simply has to do with the value of E that it was used in the equation we got. You can rearrange these things. For instance, in radioactive decay, you'll talk about half-life, but then that involves inserting magic numbers so that you can talk about decaying to 50% versus decaying to 37%. So, you win some, you lose some there. All right, well, let's try to make this concrete here with a numeric example. And also give you some idea of just how ridiculous that supercapacitor was in the video. So let's say I have here a 10 microfarad capacitor, which is a much more normal value than the 0.47 farads in the capacitor in the video. And let's say I have a 1 kilo ohm resistor here. The resistance of the circuit I hooked up was much less than that, but 10 microfarads is 10 to the negative 5 farads versus half a farad. So even though my resistance was a lot lower, we had a much longer time constant than we're going to get here. Okay, so let's say that our initial charge was 20 microcoulombs. What I want to know, so that's my little clock face, how much time elapsed when such that we got to a charge of 10 microcoulombs on the plates. Since this is a discharging capacitor, the relationship will be Q equals Q naught times e to the minus t over tau. And I'm just going to immediately put in RC for tau. Okay. So the trick is we need to isolate t by itself. First thing I can do is I'll swap how I'm writing the equation, and then I'll divide both sides by Q naught. Just doing algebra here now. We're done with the physics for a moment. Now, to isolate this t, it's stuck inside an exponential, and the natural logarithm is the thing that undoes the exponential function, what we call the inverse function. So we can take the natural log of that, as long as I also take the natural log of the other side. Now, the natural log of e to the something is just the something. So this is minus t, over, I meant to write RC there, minus t over tau. We'll just leave it t over tau. Why not? That's equal to the natural log of q over q naught. So t will be minus tau times the natural log of q over q naught. And tau, remember, was RC. So minus RC natural log of q over q naught. All right, time to stick in the values. Now, don't worry about the minus sign here, because we have less charge than we started with. So this will be taking the natural log of a number less than 1. The natural log of a number less than 1 will be negative. So with this minus sign here, we'll actually end up with a positive time. So this will be minus, we said a kilo ohm, so 1,000 ohms. We said that the capacitance was 10 microfarads, so that's 10 times 10 to the negative 6 farads. And then this will be the natural log of 10 microcoulombs over 20 microcoulombs. Now, in this case here, if you want to convert the microcoulombs into coulombs, knock yourself out, but it's an unnecessary extra step. Remember, micro is simply the instruction to multiply by 10 to the negative 6. So this is times 10 to the negative 6 here. That's 10 times 10 to the negative 6 there. I can literally cancel the micros, just like I can cancel the coulombs. And remember, if you stick numbers that have units inside of something like a log or an exponential or a trig function or anything like that, the units better cancel out. I don't know what log of coulomb means, but I do know what the log of a half means. All right, so with that, we can grind this through and we will get a fairly typical kind of value for this 0.00693 seconds or 6.93 milliseconds. All right, and that's actually a pretty typical value in a typical electrical circuit to discharge down to half of where you were to start with. Now, in the video, we saw that it was taking a lot longer than that to discharge. And that's because the resistance in the circuit was a few ohms, maybe 10 or so. And the capacitance is 0.47 farads. So that gives you a time constant of, on the order of 5 seconds-ish. And so you saw it took a very long time for the current to decay. Here, the time constant's a lot shorter, and so we decay a lot more rapidly. All right. Let's go ahead and turn our attention now to the charging case. So here, what we're going to have is a battery, switch, resistor, capacitor. And we're going to say this is initially discharged. We'll go ahead and close the switch at time 0. And so now what will happen is the battery will start to flow a current through the circuit. Technically, I'm going to draw it like so, because remember, again, this is a gap, so nothing flows through the capacitor per se, although people are usually lazy. They'll draw a line through there, but they really technically shouldn't. You're pulling electrons off of this plate, migrating them over to that plate. Remember, the electron flow is the opposite of the conventional current flow. And so initially, the voltage difference across the capacitor is 0 because there's no charge initially. So that means initially, the voltage across the capacitor, the resistor, will be the battery EMF. But as we move charge, so it will pull a big, so that'll be the biggest current we can pull. And that's because as we move charge, as we build up charge, the voltage across the capacitor will increase. That will force the voltage across the resistor to decrease, which means that the current by twinkle twinkle little star, delta V equals I times R, will also decrease. So what we're going to see happen here is the current will decay to 0 exponentially. But the voltage across the capacitor and the charge held by the capacitor will actually asymptotically approach a final value. So again, you can do this by setting up a Kirchhoff's loop law analysis, recalling that the current is delta Q over delta T, and applying the methods of calculus. I'll just go ahead and quote the result here. Again, the time constant is RC. The current will still be the initial current times e to the minus t over tau. And our initial current here we can get delta V equals I times R, E equals IR. I will be E over R because there will be no voltage across the capacitor. And then similarly, we can say that the voltage across the capacitor will be the battery EMF. And again, this is just obtaining results from the methods of calculus. This will be 1 minus e to the minus t over tau. And similarly, we can say that the charge held will be the capacitance times this voltage, so CE, 1 minus e to the minus t over tau. Okay. Again, I'm not, other than saying that they come from Kirchhoff's laws and observing that the current is going to be equal to the rate at which we're charging up the capacitor. These results come from those considerations. All right, so if we plot this out, the current will do what we saw before. So current is a function of time. So this is our initial current, which was equal to E over R. And it will do an exponential decay. And again, at one time constant, the current will be 37% of what we had initially. After two time constants, the current will be 37% of 37% of what we had initially, so 0.37 squared, etc. Now, unlike the discharging case where that was just what all the functions looked like, the voltage and the charge, voltage across the capacitor and the charge are going to look like this. So we'll say voltage across the capacitor. Let's say this is the battery EMF. This will be our asymptote. And what will happen is we will asymptotically approach. Here, let's change the color on that. We will asymptotically approach the battery EMF. Or, if this is the charge, C times the EMF. Anyway, after one time constant, 37% still the magic number, but where you'll be at here is 1 minus 37% of the battery EMF. So you'll be at 63% of the battery EMF after one time constant. After two time constants, it's going to get a little crowded right there, so I'll just do this. This will be 1 minus 37% of 37%, or 0.37 squared, times the battery EMF, and so forth. So with time, as we wait long enough, the voltage across the capacitor will match the battery EMF, which means the voltage across the resistor will have exponentially decayed to zero, which means you're not driving a current anymore. So that's why I say a fully charged capacitor acts like a break-in circuit. And in fact, this sort of thing gets used in timing applications to let something run for a certain amount of time and then stop. All right, let's go ahead and do a quick example of this. Just again to make things a little more concrete. So let's say we have a 5-volt battery here. We're going to go ahead. We'll be throwing a switch at time 0. Let's say I have a capacitor that's 10 microfarads again, and a resistor that is 1 kilo ohm. So what we had before. And yeah, I know in the previous circuit I drew it the opposite way. It doesn't matter. So let's again find the time elapsed such that our charge on the capacitor is 40 microcoulombs. Now we know that the final charge on the capacitor will be the capacitance times the battery EMF. That'll be 50 microcoulombs. So when we're 80% charged. All right, so since this is a charging situation, we'll say Q is equal to CE, 1 minus e to the minus t over tau. And again, here the whole game is going to be to try to isolate the t all by itself. So we'll go ahead and divide both sides by CE. What I'm going to do is I'm going to subtract this from both sides. I'm going to add that to both sides. Oops. And again, we now need to take the natural logarithm of both sides. So if I take the natural logarithm of this, I'm just left with the argument, minus t over tau. As long as I take the natural logarithm of the other side, which will be the log of this whole thing, 1 minus q over CE. You can't just take a log of one piece or the other. You have to do the whole thing. All right, finally, we get that t is minus tau times that natural log, or minus RC, since tau is RC, times that natural log. All right. So again here, we've already worked out this number is going to be 0.8. 1 minus 0.8 is 0.2. That's a number less than 1. I take a log of number less than 1 that's negative. They'll undo that minus sign there. So we're all good. So this will be minus, so again, 1,000 ohms, 10 times 10 to the negative 6 farads, times the natural log of 1 minus. Now here, again, just to show you a little trick, we can write 40 microcoulombs over 10 microfarads times 5 volts. Now, if you're not comfortable with this, go ahead, convert the microcoulombs to coulombs and the microfarads to farads. But if we remember that micro literally means times 10 to the negative 6, that is what it means, then I can just cancel the micros like that, and that is totally fine. And a farad times a volt is a coulomb, so that will probably you should use a different color to cancel those. Oops. There we go. So the farad is farad times a volt is a coulomb, so those cancel as well. All right, so you plug this all through, you'll get 0.016 seconds, or if you prefer, 16 milliseconds, which again is a heck of a lot quicker than what you saw in the demo. In the demo, you saw that it took a lot longer than that, and that's again because since it was a supercapacitor, we had a time constant more like 5 seconds instead of 0.01 seconds. Alrighty, so then in the next video, we'll finally get to what if we have circuits that cannot be expressed as either series or parallel. So I'll catch you over there.